Welcome to this webinar in which we look briefly at the typical problems encountered with reinforced concrete structures before moving on to take a summary view of the Intercrete product range. My name is Graham James and I'm General Manager of FlexCrete Technologies in the UK, AkzoNobel's Centre of Excellence for Polymer Cement Chemistry. This webinar is one in a series of modules on Intercrete technology and the Intercrete product range. For more information, please access the Intercrete e-learning suite. Our agenda covers typical concrete problems before we move on to discuss carbonation in some detail. We will then look at basic diagnostics for reinforced concrete structures suffering distress, and then look at the Intercrete range in summary. So first of all, some of the typical causes of concrete deterioration. Reinforced concrete structures fail for a variety of different reasons. The photograph on the right shows a catastrophic structural failure. Thankfully, a very rare occurrence, but it does happen. With regard to the Intercrete range, we are generally concerned with other influences which either affect the durability of a structure during the service life, or defects which are not corrected at the time of original construction. The most common problem is the corrosion of embedded steel reinforcement. We have all seen examples of rust staining on concrete buildings, bridges, and such like. One of the most common causes of this corrosion is carbonation, which we will discuss in more detail in later slides. The ingress of chlorides will lead to corrosion. This can either be from seawater or from airborne chlorides in a coastal location. Failure to prevent water ingress also poses a threat, lowering the resistivity of the concrete. And the importance of having the correct thickness and quality of concrete cover to the steel reinforcement is not to be underestimated. The concrete cover is the primary defense against corrosion for the embedded steel reinforcement. Fire will disrupt the surface of concrete to blow the cover off, as water in the pore structure expands during heating. Freeze-thaw cycles have a similar effect. Frozen water expands to initiate failure at the concrete surface. Impact damage, for example, if a lorry hits a bridge abutment, cover will be lost as a consequence. Chemical damage is a constant challenge with all forms of wastewater, from sewage treatment to industrial effluent. Mildly acidic water collected for drinking water can also affect concrete. Aggressive ground conditions will undermine durability, for example where there is a high sulfate or chloride content. Although not particularly common, Alkali-silica reaction affects concrete containing a reactive silica aggregate, which imbibes water, resulting in cracking as the silica gel swells. Provided it is not too extreme, some structural damage can be repaired, but if it is left without rectification, failure will ultimately occur. Earthquake-damaged structures would be a good example of this. And finally, poor workmanship, which happens on even the best planned and carefully managed construction sites the world over. We will see a couple of examples later on. We will now describe the process of carbonation. Concrete is an inherently alkaline material. As cement hydrates, it results in a pH of between 12 and 13. At this high alkalinity, a passivating layer forms on the embedded steel reinforcement to minimize corrosion. Atmospheric carbon dioxide gradually penetrates into unprotected concrete, reducing the alkalinity to a pH of circa 9. At this level, the passivating layer breaks down and corrosion starts. Corrosion byproducts, or rust, take up a larger volume than the original steel. This ultimately results in spalling of the concrete. This is the process of carbonation. In this image, we can see the effects of surface attack carbonation. The green portion at the top of the slide is the carbonated layer, which has already been influenced by atmospheric carbon dioxide to reduce the alkalinity. However, this has not penetrated the depth of the cement matrix through to the steel reinforcement. Hence, the steel is held in a passive state and no further deterioration occurs. Here we see the effects of advanced carbonation. The green carbonated layer has reached the proximity of the steel reinforcement. The reduction in alkalinity is sufficient to immediately initiate corrosion. Rust is expansive. The concrete will ultimately be ruptured, allowing free passage for the other fuels of corrosion to enter the concrete: water, oxygen, and potentially chlorides too. The rate of carbonation is dependent on a number of environmental factors. For example, because it is 10,000 times more difficult for carbon dioxide to pass through a water-filled pore, carbonation is not a threat in totally immersed conditions. However, a critical factor is the quality of the concrete cover, as poorly compacted or weak concrete will offer little defense against carbon dioxide ingress. Here we see the effects of carbonation. In the small images to the left, we can see how the lintel above the window has been broken away by corrosion of the steel reinforcement. Below that, we see a soffit where the effects of carbonation are evident with spalling. And on the main picture, the ring beam around this office building is showing obvious distress because of carbonation. Chloride contamination of reinforced concrete can bring about an aggressive form of corrosion, often characterized by some bright orange staining. In the small image to the left, we can see the effect on bridges where washed de-icing salts will cause chloride-induced corrosion. And atmospheric salts are a constant threat to all marine structures. In cooler climates where de-icing salts are used on roads during the winter months, bridge structures are particularly prone to a combination of carbonation and chloride attack, as shown in the photographs on the slide. Here, the effects of inadequate concrete cover are self-evident, as the steel is too close to the surface of the concrete, leading to premature failure. In conditions of fire, concrete is not immune from damage. The small image on the left shows what has happened when a vehicle has gone on fire in an underpass. The larger image shows the effect when a car went on fire at a toll booth crossing, causing immense damage to the concrete deck. Impact damage undermines the integrity of a reinforced concrete structure when part or all of the concrete cover is broken off. In the small image on the bottom left, we see a bridge beam has been hit by a lorry, and already we can see the signs of corrosion beginning. The larger image shows a marine dolphin which has been hit by a vessel, causing significant damage. During cold winter periods, freeze-thaw cycles can inflict damage on concrete. Here we see an example of a pavement where the surface has been completely eroded due to freeze-thaw cycling. Although uncommon, alkali-silica damage may be encountered in areas where reactive silica aggregates have been used. In this example of a highway gantry base in Japan, after repairs have been undertaken, the best way of extending the service life of the gantry is by applying a flexible waterproof coating. By preventing further water ingress, the reactive aggregate is denied the fuel it needs to produce an expansive gel. Concrete is vulnerable to chemical attack and often requires secondary protection. In the small image to the left, we can see how the surface of a concrete column has been eroded away. This is actually in contact with drinking water. The larger image shows a manhole inside a sewage treatment works where the concrete has literally been turned to the consistency of wet pulp. And finally, poor workmanship, which is the root cause of very many concrete durability issues. In this example, we can see how the concrete has been very poorly compacted, leading to large areas of void at the bottom of the shutter. This concrete is extremely weak and requires appropriate reinstatement. The last example is from a high-value infrastructure project where we can immediately see a number of issues. Looking from the top, we note significant blowholes and tie holes which require sealing. We see poorly detailed day joints and leaking from the kicker. The infilm beam appears to be of inferior quality and the substructure concrete is suffering from cracks. Unless promptly corrected, such deficiencies will, without doubt, diminish the anticipated service life of the building. We will now run through some basic diagnostics. Some of the diagnostics are very simple. By using a hammer test, the engineer will determine if there are any hollow areas in the concrete which require obvious reinstatement. Similarly, by using a chisel, scratch testing of the surface will indicate the concrete quality. Looking to the top right hand of the slide, we can see a cover meter survey being undertaken. This will establish the depth of concrete cover by checking at representative reference points. Once a reliable data set has been established, the rate of carbonation can be estimated and a preventative maintenance strategy agreed. Low cover in new construction can be quickly rectified with the application of an advanced polymer-modified cementitious coating, a 2 mm layer being equal to 100 mm of normal concrete cover. A phenolphthalein test can be undertaken by spray applying the phenolphthalein onto a concrete substrate. Where it turns purple, the concrete is not carbonated. Where it is clear, the concrete is carbonated. The image on the bottom right shows a half-cell potential test which engineers will conduct in order to establish whether corrosion is likely to occur on the steel reinforcement. Chloride analysis can also be undertaken by test houses. Here we see testing for carbonation using phenolphthalein sprayed onto the concrete substrate. Where it is purple, the concrete is not carbonated. Where it is clear, it is carbonated. We will now give a brief introduction to the Intercrete product range. We will begin by discussing what we expect to see from repair and protection systems. Firstly, we want them to be as close as possible in nature to the parent concrete. Once applied to parent concrete, we form a new composite, and it's important that the repair material or the coating behaves in the same way as the host environment. In part, to achieve this, we use polymer modification, as this improves bond, reduces permeability, and increases both the tensile and the flexural strengths. The system should be shrinkage compensated so that there is no loss of volume during curing. And in part, this is achieved through fibre reinforcement, as this is a control on permeability. The product should be easy to use, with no substrate or interlayer priming. And they should be water-based and solvent-free. And the hardening and curing characteristics should be appropriate for the circumstances in hand. Looking at the Intercrete range specifically, our first line of defence is with corrosion prevention. Intercrete 4871 is our cementitious coating for steel reinforcement protection. It passivates and protects from incipient anode effect. We have two structural grade repair mortars. Intercrete 4801, a high build hand or spray applied mortar, easily achieving up to 80 mm in a single layer, even overhead. Intercrete 4802 is a rapid setting, rapid hardening mortar for heavy duty use, typically on trafficked areas. With regard to a fairing coat, pore filler and waterproof render, Intercrete 4820 is a multifunctional mortar, an engineering quality waterproof surface finishing material for small voids or for overall rendering. The range comprises a series of highly advanced protective coatings. Intercrete 4840 is an epoxy and polymer modified cementitious coating used both on concrete to provide enhanced resistance to chemical attack and abrasion, and steel to prevent corrosion. Intercrete 4841 provides structural waterproofing. It's a complete barrier to chlorides and is effective concrete cover replacement, 2 mm being equal to 100 mm of effective concrete cover. Intercrete 4842 is our elastomeric grade of cementitious waterproof coating. Intercrete 4851 is a flowing waterproof deck coating applied at 2 mm. Its sister product 4852 is a high build version, typically applied at 3 to 6 mm. Finally, Intercrete 4890 is a decorative, protective anti-carbonation coating for atmospherically exposed concrete. It will be useful to review the common features and benefits. The materials I've described are all water-based. They are non-hazardous and odorless, and all the equipment is simply cleaned with water. There is no use of solvents at any stage in the processes. The application is very simple. There is no complex mixing and no complex application equipment required. The materials are Portland cement based and therefore fully compatible with the parent substrate, behaving in the same manner as the host environment. Application is direct either onto a saturated concrete or indeed green concrete, using only water as a primer. And the range offers rapid installation, for example with high build mortars up to 80 mm in a single layer, or cementitious coatings which can be applied between 2 and 6 mm in thickness. Continuing with the features and benefits, Intercrete cementitious mortars and coatings are fully waterproof. They are tested under 10 bar, which is a 100 meter hydrostatic head, and they have resistance to both positive and negative water pressure. Where chlorides are an issue, we can offer a complete assurance preventing further ingress of chlorides into the structure. Reinstating effective cover is simple, as our coatings will provide at least 100 mm of equivalent concrete cover. Compatibility is proven too, as we have undertaken tests and can approve use in combination with many of the AkzoNobel protective coating systems. And we have independent, wide-ranging tests and accreditations available on request, including ISO 9001 and drinking water approvals from the UK and Australia. To summarise the key attributes, the Intercrete range is genuinely innovative and highly cost-effective. The products are engineered for durable, effective protection, and they are ideal for problem-solving applications too. The Intercrete range allows for environmentally substrate preparation, and the products are suited to fast-track construction projects, allowing contractors to accelerate the construction cycle. By using Intercrete solutions, the design life of a structure can be enhanced or even matched. The products are safe for both the applicator and the environment, and they are reliable, easy-to-use products that are a popular choice for contractors. Thank you for listening to this webinar. If you would like further information on Intercrete technology and our areas of business focus, please either visit the Intercrete e-learning suite or our website through the links below.